This is the second lecture for Chapter 8 for Stats 253, and it's just one and two tail tests in general. Call the situation for confidence intervals. There was a distribution curve, and let me do a bad job of drawing that. I'm just going to do a normal standard distribution curve, and like I say, I'm going to do a bad job of drawing this. Alright, so for the confidence interval, there was a central area under the bell-shaped curve that corresponded to the confidence level. Okay. Then on the side, there were tails. Okay, and the tails were excluded from the confidence interval. And we're going to do a similar situation here, but for the confidence intervals there are always two tails. Here there may be just one tail, a left tail or a right tail, depending on how you write your alternative hypothesis. Also recall that for confidence intervals there were three types of distributions. Actually there's more, but we just considered three types: the normal standard distribution with the z-values, the student's t-distribution, and the chi-square distribution. So we'll have a similar situation in hypothesis testing. We're going to be looking at a distribution. The central area will be sort of the confidence area, confidence interval, and then there's going to be tails. Now here are some items that are different from the confidence interval. So we have, similar to the confidence interval, the area under the bell-shaped curve. It's going to be divided into a non-critical region instead of a confidence interval region. It's going to be a non-critical region, and that's going to be a region surrounding the mean. And then there are going to be one or two what are called critical regions. So to use this, the critical regions are defined. The values at the edges of the critical regions are called critical values. We used to call them z alpha over 2, but now here they're called critical values. Then you look at the new test value. This is where we're going to actually use the data that was measured that does not appear in the hypotheses. Okay. You take that test value and you check. If it falls in the non-critical region, that would be the region that's closer to the mean, then the null hypothesis is not rejected. If that test value falls in one of the critical regions, then the null hypothesis is rejected. The value of alpha that we use to find the critical region, that's going to be the area in the tails, either one tail or in both tails combined. That is the probability of making the type 1 error. And here's how the situation looks for hypothesis testing. Okay, in this case, the values have been changed into the normal standard distribution. But basically, this is the value mu naught, the a priori value from that appears in the null hypothesis. Okay, it's right here in the middle of this curve. All right. There's also a sigma associated with it, and you use that in another calculation. Okay. Around this mean is this area here called a non-critical region. And now the alpha has been chosen because you only wanted a 10% chance of making a type 1 error, so alpha is 0.1. This is a two-tail test. The total value of the tails has to add up to 0.1, so as in confidence intervals, half of it appears over here and half of it appears over here. In confidence intervals we call this value z alpha over 2, and it's actually going to have the same value, but it's now termed the right or the left critical value, CV for critical value. Okay, now the test value, the value that you measured that caused this whole experiment to happen, in this case you would change and find the z-value for it, and you would graph it here. Okay. Let's say you graph it and it's 0.75 and it comes like that. Well, it's in the non-critical region. Because it's in the non-critical region, you say this new value is not significantly different from the previously held value, so the null hypothesis is not rejected. Now let's say that z-value happens to be 2.5. It is in the critical region. Because it's in the critical region, you now say it is so significantly different from the previously held value, from the previous mu naught, that the null hypothesis is rejected. It could be over here. As long as it's in any critical region, then you're going to reject the null hypothesis. If it's over here in the central area in this non-critical region, then you will not reject the null hypothesis. Now the 1 and 2 tailed tests come from the way that the alternative hypothesis is written. So if you, for a 2-tailed test, the alternative hypothesis just says that the value is not equal to the previously held value. For a left-tailed test, okay, the null hypothesis says that the value is less than the previously held value, less than mu naught. Okay, I used theta, but you could use mu as well. Okay, and for the right-tailed test, the null hypothesis would be written this way with a greater than sign. In all three of these cases, the area of the critical region is alpha. In this case, there's 2 tails, so each tail has alpha over 2. Okay, so that the total area of the rejected tails adds up to alpha. In the next 2 cases, the area of the, in this case, left tail or the right tail is going to be alpha itself. So sometimes you divide by 2. When it's a 2-tailed test, you'll do that. When it's a left or right tail test, you do not divide alpha by 2, because all that area is going to be concentrated either into the left or to the right. So here's a 2-tailed test because the alternative hypothesis has a not equal sign in it. So if you want to make a 90% or have a 90% confidence, then the alpha is 0.1. Alpha is 1 minus the confidence level, right? And now these critical values are from the table in the lecture notes, but I will show you later how to find them in general in R. So these are going to be the critical values, and you notice this is a 2-tailed test, and the critical values have plus and minus sign in front of the value, in front of the number. So again, the previous value is the mean. In this case, it's been changed into a z-value, so it's 0. And then the test value, you take the test value and you change it into some z-value and you graph it. And if that z-value, in this case, say is 1, then it is so close within the, well, it's in the non-critical region about the previous value that you say the null hypothesis will not be rejected. If it's out here in the tails, then you're going to reject the null hypothesis. Now this shows for conversion, of course, to the standard with mu of 0 and be a standard deviation of 1. This isn't necessarily, let's look at it as though it were in actual data values. I'm going to replace the scale here. Let's say that, whoops, I didn't intend to do that. Okay, here we go. Okay, we're going to forget this for right now, these z-values. And let's say the mean for your data is 25. Maybe that's the speed that people go along a certain road somewhere. Okay, so let's say that the previous mean for the speed was 25 and it has standard deviation of 5. Alright, so this would be 25 instead of 1 here. This would be your 30, and this value up here would have been 35. Okay, and going in the other direction, I'd see it. Whoops, here's the 20 goes here, and here would be 15. Okay, so say this was your bell-shaped curve, not changed into z-values, but simply your bell-shaped curve. Okay, and now you're having a two-tailed test, and you come up with a critical value of, well, so that your area is mapped out is whatever it is, 0.1, say. Then right here would be your critical value, and it could be in actual units, not necessarily in the units for the z value. And now if your new mean was, say, 30, and you graphed it in this case, you would see that this 30 still lies in the non-critical region. So, so for this case, the null hypothesis, which is, would not be rejected. So I just wanted to show it to you with some actual values instead of the z-values. But many times it's transferred, everything's changed into z-values. And that's, of course, if you want to use the tables, you have to do that. In R, you have a little more flexibility, and you don't have to change everything into z-values. When you're using the normal standard deviation, normal standard distribution, if you're using the t distribution, then yes, you have to change everything. You don't use the original units. So here's an example for a left tail test. Here's your alternative hypothesis with the parameter less than the value for the null parameter. Okay, and depending on your alpha, you'll have different critical values. These are given in the notes, and again, I'll show you how to find them in R. Okay, so in this case it's a left tail test. You see these are negative signs, so this whole area contains all of the is equal to alpha. It's not split between two, between two tails. And it's the same procedure. If your test value lies, for example, up here, this whole area is in the non-critical region. Everything above the z is z of 0. The mean is the non-critical region. So anything up here would be an acceptance of the null hypothesis. If the test value is over here, then it's a rejection of the null hypothesis. And this is just the third case. Alternative hypothesis written with a greater than sign. In this case it's going to be right tails. So here's a right tail up here. The entire area of alpha is concentrated in the right tail. I wanted to make a comment about the homework. On the homework in the second page, or third page, it's the second page, there was a setup to write confidence, correct decision, type 1 error, type 2 error, and the wording there is a little bit unfortunate since we talk so much about rejecting the null hypothesis. And it was, the table looks something like this. There was an H naught is true, null hypothesis not true. Okay, and here was the drug rejected, and that's, why don't you, instead of saying rejected, just cross that off and say drug pulled from the shelves. Okay, so drug is pulled from the shelves, and here for the other one it's saying drug is accepted, which is, again, like I say, it's using one word in two different contexts, which it's confusing. Say the drug is added to the pharmacy. I think that will make things clear. So H naught, I think the null hypothesis was that the new drug was ineffective. And here it's that it's effective. And so now you can fill in what are the correct decisions. If it's ineffective, you probably don't, why put it on the shelf? If it is effective, then you'll want to add it to the pharmacy. So you're going to get a correct decision here. You get a correct decision up here. Okay, Now, where's your type 1 error going to be in this case? If it is effective, but I throw it out. Wait a minute, what have I done here? No, I fooled myself here. I did it wrong. Okay, let me start over. Okay, so this is your ineffective drug, and you can write notes on these graphs too if you want. And this is an effective drug. Here's the case where we're going to take the drug and we're going to pull it. And now we're going to take this drug and we're going to add it to the pharmacy. Okay, if it's an ineffective drug and I pull it, that's a correct decision. If I add it to the pharmacy and it's an effective drug and I add it to the pharmacy, that's a correct decision. Okay, this is the null hypothesis, because we're assuming that it's true. So we say it's an ineffective drug, but we add it to the pharmacy. So by adding it to the pharmacy, we are rejecting the null hypothesis. So this is your type 1 error. Okay. And now you pull it when it was effective. You've got a type 2 error. Okay, but I think you can figure this out. It's not that hard, but I think it's better if you replace the word reject and accept with pull it from the shelves and add to the pharmacy.